are told later in the future to calculate or to convert a radian value to a degree value or a degree value to radian value. This is just how to do that. So let's go to the next one. We say relationship between linear and angular displacement. All this you need to know. Now when I say angular, a body moves from here to here, A to B. This is what we call linear displacement. It's not moved, it's not going through an angle. Do you understand? Move through an angle x, distance x centimeter, not through an angle. So it's a linear displacement. But if the body tends to move with an angle that is curved with respect to this angle, this particular displacement is what we call angular displacement. Not linear, it's angular displacement. So on the angular displacement now is now measured with what? Theta. So if you want to with respect to what? Radius r. So angular displacement x is automatically given as what? Theta dot r. Meaning that your theta is your angular. X is your what? Linear displacement. While your r is the radius involved. So that's the formula relating your what? Linear displacement and your angular displacement. So also your velocity. Your normal velocity will equal to what? Angular velocity dot r. Where your what? Omega is what we call angular velocity. This is what we call omega. So v equals omega dot r. So we also have your acceleration. Your acceleration will equal to alpha dot r, where your alpha is your what? Angular acceleration. So these are the three values you must what? Note very well as we proceed. We also make use of it when we start doing our what? Calculation. But another wonderful thing about angular acceleration is angular acceleration can also be given as what? Normal acceleration can be given as velocity squared dot r. So these are the four formulas you need to know when it comes to your simple harmonic motion. Let's look at some terms that are associated with simple harmonic motion. Number one, we have what we call period. What is period? Period T. I was giving the mathematical formula for period for your general supermodel known as 2 pi 2 pi square root L over G. That's one formula for period. But as we proceed, you'll be seeing some other formulas. Now, what does that period mean? It is the time required to make one complete oscillation, to make one complete revolution about a point of reference. The time you need to make one complete, that is, decide to move from here. This is like a circle. Are you seeing it? The time you need to move. So this is one complete revolution. It's like your earth turning all around. The time for you to move, to make one complete turning point, that time is what we call period. Are we seeing it? The time required to make one complete revolution about a point of reference is what we call your period. Now let's proceed to the next one. We have frequency. Frequency, it is the number of complete revolution. Are you seeing it? They are all somehow related. Period is the time required to make one complete. While frequency is the number of what? Complete revolution you make is your frequency. Are we seeing it now? So they are inversely proportional to each other, meaning that period T is the inverse of frequency. We said we have what we call frequency F. You understand? Now frequency is measured in S. Period is measured in what? Seconds. So inverse of period is frequency. Now inverse of frequency too is your what? Your period. So these are the two formulas relating your what? Period and frequency. So if you look at it properly, you realize that, remember, if you have to recall the definition again, period is the what? Time to make one complete oscillation or revolution. While frequency is the number of revolution you make. You understand? The number of that revolution you make, the total number of it is your frequency. While your period is the time you need to make one complete revolution. Now let's go to the next one. Amplitude. Amplitude is defined as a maximum displacement of a body from an equilibrium position. When I say equilibrium, that is, I have this body now, pendulum ball. Let's say this is the starting point. If it goes this way, it goes this way and comes. By the time it moves forward and backward, little by little, it will be reducing. Now, the maximum displacement here is what we call the amplitude. The maximum displacement an object could go, you understand, from its reference point is what we call the amplitude. So that is what we have in the definition over there. So there are a lot as regards when it comes to your simple harmonic motion. So many things needs to be known. Now, let's go to how do we derive energy? Energy notation for your simple harmonic motion. Recall that your force of a spring, force of spring, we use spring this time around. Force of spring is known as constant per dot E. What does E mean? Extension. Do you understand? Your spring constant times your extension. So your work done, remember we said work done is force times perpendicular distance, and that distance could be likened to the same extension. So by the time you start this here, you have your Ke all squared. You understand? So from that, you now know that it is. So here we are looking at what we call average force. If it's normal force, you use this full formula. But if it's an average force, you now insert them in. You'll be able to have half Ke squared. So this will now be your work done. So that work done will now automatically equal to the energy of your simple harmonic motion. So energy of simple harmonic motion is half Ke squared. So that is how we derive our energy for simple harmonic motion. So it goes on and on like that. So you need to, number one, first get the actual definition of simple harmonic. Then the second part is you must know all these terms often. Then you must also know the derivation of this energy. You'll be able to derive the energy, you'll be able to know those notations, and then from there you'll be able to now apply them to your simple harmonic motion problem. Now let's go to what we call damped vibration. Now, in ideal sense of simple harmonic motion, it's supposed to vibrate with maximum amplitude. But unfortunately, this is not possible because the amplitude of the oscillation continues to decrease gradually until the vibration eventually stops. So if we look at that, you realize that vibration will continue. But as time goes on, vibration tends to stop. Vibration tends to reduce. Now, the process by which the vibration a body is experiencing or is experiencing, let me draw a graph there so that you understand what I'm actually trying to say. You have something like this, you realize that it goes smaller and smaller and smaller and smaller till eventually, are you seeing me? So there is a vibration here, upward. There is also a vibration here. Now, at this region, vibration tends to be very high. Why? Because the object tends to go even towards the positive y and negative I. You understand? Positive y-axis and negative y-axis. But as it goes forward and forward, the vibration tends to balance it. So at the point where vibration is no more experienced, it says that body has undergo damping. Damping is the removal or reducing of vibration of a body. But let's continue with that statement. It says, take for instance a simple pendulum ball. It vibrates for some time and eventually stops. Some motion in which the amplitude decreases until it eventually stops is known as damped vibration. So you can see from the chart there, you'll be able to see what we call amplitude. The amplitude is being known, and before you know it, the amplitude reduces until it does not exist anymore. Now, what we call forced vibration. So they are both almost the opposite of each other. For damped vibration, the vibration eventually leaves. But for forced vibration now, the vibration does not leave. Do you understand? Instead of the vibration to leave, the vibration continues. You understand? It tends to, each time the vibration wants to go down, by the time you go to this junction, another external body will help vibration to go up again, and the vibration becomes larger again. So the vibration of that body does not goes up. So for first vibration, let's see the definition. When an oscillating object experiences slower vibration continuously, bringing about a stop. Instead of vibration to be stopped, are you seeing it? The system is being influenced by some external forces, which enables continuous vibration of that system. So that is what we mean by forced vibration. This question is always being asked in your SSC, WAEC. You know, you need to have the proper knowledge of what we mean by damped and forced vibration. So let's take these little exercises before we jump into the next topic. Now, number one, we have a particle moves 240 rpm on a circle of 2 meter radius. Find its period, angular velocity, linear velocity, and its what? Acceleration. Now, the body is moving at 240 rpm. What's rpm? Revolution per minute. So for every 1 minute, it's moving at what? 240. Are you seeing it? Now, the radius of the circle is 2 meters. Are we seeing it? Now, if the actual value of the displacement is 240 and the radius is 2 meters, how do you now obtain your period? Remember, period is what? 1 over frequency. Right? Now, if period is 1 over frequency, this is the frequency, 240. So it's going to be 1 over 240. Are we seeing it? So from there, you obtain a value. Shake it. So from there, you have 0, 0, 0. By the time you insert them, you'll be able to have a value for the